to our senior executive liaison for outreach, Natasha, who is going to introduce the speaker today.
Well, it's a pleasure to reintroduce you after the beautiful talk we gave yesterday. So I'm happy to introduce again Amelia Salazar from Brazil. She's giving the first talk in the frontiers, IMSA Frontiers in Mathematics, and the talk is entitled on local integration of group brackets.
Thank you so much for the introduction, and thank you again for the invitation, especially Ludwig. It's a pleasure to be here. So, okay, so today I will tell you about a little bit of my research. It's again in these directions of foundations of the theory for groupoids and the algebroids. And here I will also address Lister's problem about integrating the algebras but now to local groups. Okay. So what I will do today is that given a algebroid, I will construct explicitly integration to a local groupoid. Okay. So and this is also relevant because many geometric structures that are kind of difficult to understand. You want to desingularize them, okay? And you use groupoids to do that in some sense that I will explain later. So this type of construction of local groupoids integrating algebroids will give you desingularizations of some geometric structures. Okay, so let me just quickly remind you about my object. So I work with the groupoids. These are two manifolds G and M. G, you can think that M is the space of objects and G is the space of arrows. And then you have two surjective summation, source and target. Sigma is the source and target is tau, which tells me the beginning of each arrow, the source, and the end of the arrow, the target. Okay. You also have a partial multiplication defined on arrows such that the first one ends at the beginning of the second arrow. And for this multiplication, you will have units, right? For each object, I will have a unit for the multiplication, and I will have inverses. So this unit, this map, is an immersion, so I will always think of M inside of G as a submanifold. Okay? So a prototypical example is this fundamental groupoid, where the arrows will be paths, modulo homotopy, and you can concatenate two paths whenever the first one ends at the starting point of the second one. Okay? So examples are, as I told you, the groups are the same as leading points over a point. Also, if you are interested in working with PDEs, whenever you have a Lie pseudogroup, so out of a Lie pseudogroup, you can produce a groupoid, which is made of jets of the elements of the pseudogroup. Foliations also have groupoids associated to them. And as I told you, symplectic groupoids appear in the work of Alan Weinstein when he was trying to desingularize Poisson manifolds. Okay, so the infinitesimal counterpart of the groupoid are the algebroids. So these are vector bundles A over M together with a Lie bracket in the space of sections, and a map from A to the tangent bundle of M that satisfies this Leibniz condition. Okay, this Leibniz condition will imply that this anchor will respect the Lie bracket with respect to the sections of A and the Lie bracket on the space of vector fields. Okay, and this also tells me that the image of the anchor is actually an evolutive distribution. Okay. So examples again, the algebras are the same as the algebroids over points. Foliation also give me an example of algebroids. Actions like actions of a algebra on a manifold also gives me a algebroid. And as I told you yesterday, Poisson manifolds are encoded in a algebroid on the cotangent bundle. Okay, so why did I tell you that the algebroids are the infinitesimal counterpart groupoids. So given groupoid G, I can consider what I want to do is to reduce our over M so that the sections are actually right invariant vector fields of G. Okay? Right invariant vector fields of G are determined by their values on the units. Okay, so my bundle is actually the kernel of the differential of the source restricted to the units. Okay? And then each section of A would give me a right invariant vector field given by this formula. And as soon as you realize that right invariant fields are closed under the Lie bracket, then you can induce a Lie bracket on the space of sections of A. Okay? Examples, again, if you take a Lie group, the Lie algebroid associated to the Lie group is the Lie algebroid of the Lie group. If you have, again, the affiliation, you take the fundamental groupoid of the affiliation or the holonomic groupoid of the foliation, the algebra will be the foliation itself. Or if you have a symplectic groupoid and then you look at the associated algebroid, what you find is that this is the Lie algebroid of a Poisson structure on the base. Okay, so whenever you have a symplectic groupoid, it will induce a Poisson structure on the base. Okay, so list third theorem. This is so this construction of the Lie algebroid of a groupoid leads us to this question of list third theorem. So here in a algebroid, is there a Lie groupoid that integrates the Lie algebroid? And the answer is that this is not always the case, but the abstractions are well known and they are topological. They were described by Marius Craig and Loya Fernandez in a paper in 2002, I think, or 12, I don't remember. And then, well, this is a yesterday I gave you a counterexample of a transitive Lie algebroid, which is not integrable. Okay, transitive meaning that the anchor was rejected. This is another example. So if you take this Lie algebroid given by the tangent of S2 times R, okay, so the anchor will be the projection to the first component. So now you see that the lift of the involutive distribution on Tm are just copies of S2, okay, and then you have this Lie bracket. Okay, so what happened is that if this algebra would be integrable, then the restriction of the algebra to each of the lists would be integrable as well. Okay, but what happened here is that now if you look at these restrictions of the algebroids, they are transitive. And as I told you yesterday, transitive Lie algebroids, if integral would integrate to the Artesian groupoid of a principal G bundle. Okay. And following the example of yesterday, what you realize is that this principal for each key, right? So AT is a Lie algebroid of the MT. The principal G bundle will have a structured group given by R mod lambda, right? Lambda T, where lambda is T times Z. Okay, you realize this by doing kind of the same computation that I did yesterday. So you see that when T goes to 0, somehow these circles will so what you get is that you have circles, and at some point at 0 you have just the real. So it's like give you an idea why they don't fit together to form a Lie groupoid. Okay, because at 0 you have like something that changes dramatically. Okay, of course you can formalize this, but this is the intuition. Okay. Also, if the whole thing would be integrable, the restriction to the list, the groupoid restricted to each list will be the Lie groupoid integrating the list, the algebra restricted to the list. Okay. Okay, so now that we understand that that this is not possible, then we go back to the original work of Lee. He originally proved that given a Lie algebra, he could integrate it to a local Lie group. Okay, and his proof was kind of related to the BCH formula that I told you yesterday. And he used finite dimensional techniques, and his construction was very explicit. So what about groupoids? So one of the byproducts, so this was in 2003, one of the byproducts of Freilich and Fernandez tell us that local integration is unobstructed. You can always integrate it to locally groupoids. So local groupoids means that all the structure of the groupoid is defined around the units, in a neighborhood of the units. Okay? But the proof it shows only existence. Okay, it's not constructed, and they use infinite dimensional techniques. Okay. So actually, so in this paper with Alejandro Cabrera and Marcut, what we did was to address this problem and solve it. And our construction was very explicit. Okay, so given a algebroid, we constructed a locally groupoid, and this locally groupoid only depends on the algebroid data. Okay, and it uses finite dimensional techniques. Okay, so it's very natural somehow. So actually, what we did was the following. So we have two results, two main results. The first one says that whenever you have two locally groupoids and you have a map between the algebroids, okay, a morphism of the algebroids, then you can integrate this map to a locally groupoid morphism. Okay, and the locally groupoid morphism is unique around the units and is defined by an ODE, so it's very explicit. Okay, and the second theorem says that any algebroid is integrated by a locally groupoid, and the construction is very explicit. Okay. So what I'm going to do now is to show you the ingredients that I use to prove the first integrability result of morphisms. Okay. So I started saying right?
Yeah.
Okay. So okay, so the first ingredient is the Reperto form. Let me write something here. So the Reperto form, you can look at it in the following way. So you have a locally groupoid over M, and then you have this map, the division map, okay, that captures all the multiplication. So it encodes the multiplication. The division map, why do I talk about this division map? The division map is a morphism of Lie groupoids. Okay, so I have here the division map, which captures the multiplication, and is a morphism of Lie groupoids, where the first groupoid is just the fiber product with source, the first projection, and target, the second projection. Okay, and you see that this division map covers the target. Okay. On the other hand, I have the Reperto form. And the Reperto form, so here I'm using this notation, the sigma of G just denotes the kernel of the differential of the source. Okay. And then the Reperto form, what it does is that it takes a vertical vector field, so something that is tangent to the source fibers, and then it translates the vector field to the units. Okay, but one way to see this Reperto form is that it's actually the Lie algebroid morphism that comes from delta, okay, from the division map. So it's just the differential of the division map restricted to the algebroids. Okay, so the Reperto form is the Lie of the division map that goes from this space to A. Okay, so saying that, it follows directly also that that the Morel-Cartan form is a Lie algebroid map, so it respects the Lie bracket. Okay, it's the unit is the identity when we restrict to the algebroid. This is the second condition, and the third condition is that it's a fiber-wise isomorphism. These are kind of the main properties of the Morel-Cartan form. Okay. Now, okay, so the Morel-Cartan form was the first ingredient. The second ingredient was tubular structures. So what happened here is the following. So you have the source, which is a summation, okay, and you have a splitting of this summation. So as soon as you have that, then you can split the tangent space of G at the units as Tm plus A, right? So you can identify the Lie algebroid with the normal bundle of N inside of G. Okay? A tubular structure is just an open-end base of my algebroid inside of G along the source fibers. Okay? And so it should satisfy that the zero section goes to the units, and that the differential, when we restrict it to the algebroid, is kind of the identity on A. Okay? Of course, they always exist because I'm identifying A with the normal of N. Okay? But as soon as you have that, you realize that you get a scalar multiplication defined in a neighborhood. So something that I want to point out here, whenever I write an arrow, it means that it's only defined around the zero section or around the unit section, because here I'm talking about germs. Okay, it's everything around the zero section or the units. Okay, so what I was telling you is that when I have a tubular structure and a groupoid, I will get a scalar multiplication on G along the source fibers, right? The one that is inherited from the vector bundle A. Okay. Okay. So about morphisms. Okay. What happened with morphisms? Okay. So let's say that you have two local groupoids and you have a germ of a Lie groupoid morphism. Okay. Because it's a Lie groupoid morphism, it respects the multiplication. So this implies that F will commute with the division map. Okay, the division map of G1 and the division map of G2. Okay. Now that we know that it commutes with the division map, and we know that the Morel-Cartan form is actually the differential of this division map, then it follows that you have this commutative diagram. Okay. When you take the differentials. Okay. So because you have this commutative diagram, then you get this equation in blue. So here you realize that this P of K of T is just TF applied to this vector. Right? So I'm just writing down the commutativity of this diagram. Okay. So what I see here is that actually I can define the image of F applied to G as a solution of an ODE. Okay, so I'm writing here this curve K of T, but this is the ODE that it should satisfy. Okay, and then F applied to G is just the solution of this ODE at time 1. Okay, as soon as you have that, then of course it's not surprising that you have the following result. Okay, so suppose that you start with the Lie algebroid morphism. Okay, and suppose that these algebroids come from local groupoids G1 and G2. Okay, so as soon as you fix a tubular structure on G1, you will get this ODE in terms of the model pattern form. Okay. You can always solve this ODE because theta 2, as I told you, model pattern forms and are fiber-wise isomorphisms. You can invert the model pattern forms. Okay. So what we get is that you can integrate this Lie algebroid morphism to a Lie groupoid morphism F, and this is unique around the unit section. So a corollary comes from the following. So suppose that you have G1 and G2, and they have the same algebroid A. So now you have the identity here, and you can integrate it, okay? Around the unit section. And you can also integrate the identity in the other direction. So this gives you this corollary that any two locally points integrating the two Lie algebroid are isomorphic around the units. Okay. Okay. Now, let me tell you about what happens when you integrate algebroids. Okay, so we start again with the algebroid A over M, and then what we do is that we will construct a locally groupoid, right, whose space of arrows will be precisely A, okay, the algebroid itself. And this algebroid will only use this, this locally groupoid will only use the algebroid data and the use of an algebroid spray. What is an algebroid spray? An algebroid spray is a vector field on A satisfying two conditions. The first condition is that this vector field is homogeneous of degree 1. Okay. So if I consider multiplication by a scalar P, this tells me that the push forward of this multiplication by T, if I push forward B, then this is T times P. And the second condition is that V lifts the anchor of A, meaning that if I project the vector field base, let's say V at the base of A, this is the same as the anchor of A. Okay? So examples. If you have the algebra, there is a canonical spray, which is just the zero vector field. Also, maybe you are more familiar with the second example. If you have A equal to the tangent space of a manifold, and this manifold is a Riemannian manifold, then there is this notion of geodesic sprays, okay, which are vector fields on the tangent bundle of M, so that the flow respects the metric, and they have the property that if you project down the flow, then you get geodesic. Okay, and an observation is that these Lie algebroid sprays, they always exist. How can you produce one such a thing? So if you have a linear connection on A, this is something horizontal, right? What you can do is that whenever you have a point on A, you can lift row of A, okay? You can lift horizontally row of A. This will give me a vector field based at A, okay? Okay, so what we do is the following. So when we choose a spray, we construct a locally groupoid given by the following data. So as I told you, the space of arrows will be A itself. Okay, the unit section will be just the zero section. The source section will be just the projection of A to M. The target will be a composition of the flow at time 1 with the projection, and the inverse will be just minus the flow at time 1. Okay. The multiplication, which I will describe later on, will be given by an ODE. Okay. In terms of this of this form that will play the role of the Reperto, and it's called the realization form. I will tell you how to construct it. And this ODE, it only depends on this realization form, right? And this flows from this type of equation. Okay, so I told you that this realization form will play the role of the Reperto form. So let's see what we should get there. Okay. Yeah, so first, before telling you about this realization form, there are some properties that are easily deduced. Okay, so the axioms that only involve these maps U, sigma, tau, I are easily deduced from this formula. Okay. For example, so one observation is the following. If you have a vector field that is homogeneous of degree 1, this is equivalent to say that the flow satisfies this equation. Okay, so if I flow at time t and then I evaluate at SA, then you get S times the flow at time S time t. Okay, so when I plug in S equal to 0, I get that this flow is the identity on the 0 section. Okay, because it's the identity on the 0 section, I know that around the 0 section, the flow is defined until time 1. Okay, around the 0 section. So from here you get, for example, that the target tau is defined around the unit section, and also the inversion is defined around the unit section. Okay. For example, one of the axioms is to show that the target of the unit at x is x itself, and this follows just by noting that the flow is the identity of the 0 section. Okay, this first equation. Okay, and all the other axioms that I wrote there, they are easily deduced. Okay, so I was telling you that I have to construct this realization form that will play the role of the Reperto form. So remember that I have my groupoid will be A itself, right? So sigma will be just the projection, and tau will be just the Q composed with the flow at time 1. So here, when you have the Reperto form, the Reperto form actually covers the target. Okay, this was something that I forgot to write there, but I think I explained this to you. Okay, so if we apply this construction, but now to this object, what we see is that we need to produce something here, right? Covering this Q composed with this one, the target. Okay, and as the Reperto form does, it should have 3 main properties. First of all, it should be a Lie algebroid morphism. It should respect the bracket. Okay. Here the bracket is just, I mean, you have this colligation given by the Q fiber, so you have the bracket restricted to this colligation, right? The second thing is, if I restrict to the units to the 0 section here, right, I should get the identity. And the third thing is that it should be a fiber-wise isomorphism. Okay, so how do I do this? I can look at the following exact sequence of algebroids. So given this algebroid A over M, I can define this pullback algebroid on top of A, which is an extension of my algebroid A by the vertical vector fields. Okay. This is an exact sequence, so on top, if you go to inclusion and then you project, you get 0. And on the base, you get just the map Q. So of course this map will not work, right? Because you need something which is kind of similar, but again, looking at the base of the map of the base, I mean, they are very different. So what you do is the following. Remember that I started with the spray. Okay? The spray satisfies the condition. The condition that I use here is that it lifts the anchor. Okay? So when I project the spray, when I project dq of dA, I get the anchor of A. So this tells me that I can produce a section of this new algebroid Q of A. And it's very natural, it's given by this equation. Okay? So there is some generic construction for the algebroids, which is you can think of that of the algebroid Tm, which does in the following. As soon as you have a section of an algebroid, think of a vector field, then I have the flow of this section, which is a Lie algebroid automorphism. Okay. So so I have the flow of this section at time 1. It's a Lie algebroid automorphism. Okay, the one that I drew in the middle, and it will be defined around the unit section as well because of the homogeneity of B. Okay. So if I take this composition, and actually this flow of B hat will project to the flow of B at time 1. Okay. So if I look at this composition, I have things that come from free. For example, I already know that this composition will be a Lie algebroid morphism. Okay, because it's a composition of Lie algebroid morphism. The second thing is that also by construction, it will cover the map that I want. This one. The target that I defined. And the other thing is that, okay, so the first conditions that theta is the identity when I restrict to the algebroid and that it's a fiber-wise isomorphism, it will come from the homogeneity of B. Okay, this is, I will not prove, it's just a computation. Okay. And then, but then what happened is that actually we have like a very explicit formula to define that gives us this realization form. You can ignore what is written there because I just want to compute it in a very simple example, which is the following. So take a Lie algebra and take the zero spray. Okay. So this map alpha of epsilon, which was alpha of epsilon are sections, and then you evaluate them at this other point. Anyway, it doesn't matter. So this alpha epsilon of T should be elements of my Lie algebra. Actually, they don't depend on T because I'm taking the zero spray. And the flow of the zero spray is the identity, of course. The flow of the vector field that is zero is the identity. Then what I get is this that alpha epsilon of T is just A plus epsilon B. Okay. Now the flow of alpha 0, which is A, is actually this map. Okay. So let me just define how you compute flows of sections or of elements. Okay. So the flow, here I'm taking U equal to T minus S. So the flow of an element, I don't know, in this case was A. Okay. This is, as I told you, an algebra morphism that satisfies the following equation. So if you take the differential, T minus apply to any element of my Lie algebra, what I will get is that this is this flow applied to the Lie bracket of A and B. Okay, so you can actually do the computation with this P of UA equal to E2 minus U out of the adjoint of A, and you will get this formula. Okay. And then what you get is that the Maurer-Cartan form applied at the point A, applied on B, is given by this integral. Okay? If you integrate that, then you get this formula here. When I'm taking the division, is that around the unit, the adjoint of A will be inverted. Okay, that's why I'm taking the division. This is something that that you have to check. For A small enough, then the adjoint of A is invertible. Okay. I think this is something that I showed you also yesterday. I mentioned that. Okay, so what we get is the following. So given a Lie algebroid over M with projection Q, I didn't write it down. Then actually what you get, so these maps, the zero section, the projection of the source, and the target inversion, and so on, together with this multiplication defined by this ODE, the ODE is in terms of this realization form. Okay, these are the structure maps of a locally groupoid structure on A. Okay, and actually the Maurer-Cartan form of this locally groupoid is my realization form. As soon as you prove that, then this shows that the Lie algebroid associated to this GB is A itself as a Lie algebroid. Okay? So out of A, we produce a Lie algebroid that only depends on the Lie algebroid, sorry, that integrates my Lie algebroid, that only depends on Lie algebroid data and a spray. Okay. So let's look what happens. Let's look at some immediate consequences. Okay. So suppose that you have an algebroid over M, and you choose a spray. Okay. And suppose that you have any other locally groupoid that integrates A with my Maurer-Cartan, this theta of G. Okay. Then, out of this data, you can define this exponential, this spray exponential. Okay, this spray exponential will be a map from A to G, okay, given by the solution of this ODE. Where here I'm using the flow of B and the Maurer-Cartan form of G. Okay. But what I'm doing here actually is the following. So remember that we already have integration of morphisms of Lie algebroids. Okay. So I have here A, right? I have the identity map. Then I have two Lie groupoids, locally groupoids integrating A, G, the one that I started with, and then the spray groupoid, which as a space of arrows is A itself. Okay. What I'm doing here is that I'm just integrating the identity map. Okay. So actually, what I'm getting here is that if I look at the structure, the Lie groupoid structure of my spray groupoid, okay, this will be the exponential of B will be a local Lie groupoid isomorphism. Okay. And so this is nice because it's telling you that any local Lie groupoid is isomorphic to a spray groupoid. Okay, somehow the spray groupoid gives you a local model for Lie groupoids integrating an algebroid. Okay. So let's look at this very simple example. So take your Lie algebra again. Yes, this is what it's telling me. So the spray groupoids are the models for any integration. Okay, so let's look at this very simple example of the algebra, which actually, I mean, it's very simple as soon as you look at it like this, but then you realize that there are some very interesting formulas showing up. Okay, so if you look at the algebra and you consider the zero spread, I already described to you the modified the realization form associated to the zero spread. Okay. So the ODE that defines the multiplication on G, okay, after inverting this realization form becomes this equation. Okay, and this equation is defined if A is small enough. Okay, it's a kind of a computation. I think you can find it in some books. If you start to write up, if you look at the power series of this k of t, you will realize that the formula, the multiplication, only involves a, b, and the brackets. Okay, it's an infinite power series, but it also only involves that. And again, if I start with the LIGU, with the algebraic G, and I look at the exponential of this spread, of the zero spread, I will just get the exponential. Okay, so this is kind of cute. Okay, so so some application. So is there any question? Because I think I went a little bit fast. No, is it clear? Okay. So let me tell you a little bit about this application to geometric structures. Actually, we have a second paper where we apply these constructions to desingularize many types of geometric structures. Okay, those that are described using algebroids. Okay, let's take this example. Let's start with a Poisson manifold. Okay, then what is asymplectic realization? Asymplectic realization is asymplectic manifold together with a surjective summation sigma, so that sigma is a Poisson map. So in a Poisson map means more or less that sigma pushes forward the symplectic form to my Poisson bivector phi. Okay. And when I have symplectic realization, they are very useful because somehow Poisson manifolds are very wide. Okay, the geometric structure is very intricate, so I can use Poisson symplectic realizations to understand these Poisson manifolds, because Poisson symplectic manifolds are much easier to handle than Poisson manifolds. Okay. Now what happens is that you know that a Poisson manifold is encoded completely on a algebroid, on the cotangent bundle of M. Okay. So what I can do there is to choose a Poisson spray, which is a Poisson spray is an algebroid spray for this algebroid. Okay. So when I choose my Poisson spray, I can integrate this algebroid. First thing. Second thing is that if you look at the cotangent bundle, you have a canonical synthetic form, right? And using this formula, which is not like a lucky guess, it was not a lucky guess, it was just applying our integration of morphisms in some other groupoid somehow, in a bigger groupoid. We get these two forms, okay? And these two forms will be symplectic around the unit. Okay. And these two forms is not only symplectic, it will be multiplicative, it's compatible with the multiplication on this spray groupoid. So what I get is a symplectic groupoid. Okay, G of B together with this part, with this omega will be a symplectic groupoid. Okay. And sitting above M, okay? And whenever you have this symplectic groupoid, what happens is that the source, which in this case is just the projection, will be a symplectic realization. So that's a way to desingularize, as I told you, a geometric structure. In this case, a Poisson structure. Okay, and I not only am getting a symplectic realization, but I'm getting a symplectic realization which is super rich because it has this multiplicative structure. So it has a lot of geometries on how to deal with this object. Okay, but you can apply it to many other different types of geometric structures. We have a paper where we describe, like, I don't know, Dirac, contact, Jacobi, like many types of geometric structures. Okay, so I think I went a little bit too fast, but it's okay because we are tired. So thank you very much for your attention.
So I have a favorite Poisson manifold, which is the dual of a Lie algebra. What is the symplectic groupoid? What is the symplectic realization which your procedure produces in that case? Does it have a nice name? Is it something I was already familiar with?
No, I don't think it has a name. But I mean, it would be. It would be G star, right? Right, because the Poisson structure is on the dual of the Lie algebra, right? So this will be my Lie algebroid, right? It's on the tangent of G star. Sorry, it's on the tangent of G star. But I'm sure you can. I think it should be very related to the BCH formula. Because it's somehow right. So what you do is that somehow you take the Lie algebra, and then out of that you produce the linear Poisson structure, which is completely encoded in the bracket of the Lie algebra. And you already know that when you integrate a Lie algebra using this type of procedure, you get the BCH formula. So you get something related to that. I haven't done the computation, but I'm sure.
Cool, thanks.
You're welcome.
Other questions? Yes. Ernesto?
Yeah. Well, here I got a little bit closer. So the hypothesis of the symplectic relaxation was nothing.
Yeah,
So,
it's only that what you get, the thing is that you don't get a global groupoid, you only get a local groupoid.
but if it's not compatible, presumably the thing and the thing.
It's a neighborhood. It would be a neighborhood of the zero section. Yeah, I mean, it could get thinner, but it would be an open neighborhood.
And so you have this map.
Mm-hmm.
And presumably there is regions that are typically symplectic.
Sorry, the what?
So in a Poisson network, presumably some regions will be just symplectic.
Some leaves, you mean? Some leaves of the Poisson manifold.
Well, no, I mean very none. And if a region of the symplectic of the Poissonian to what also the symplectic, classes or something happens.
Yeah, I think what you are telling with what I understand is okay. So the leaves of Poisson manifold are symplectic, and then you look at the restriction. I think. Yeah. So if you start with a symplectic manifold, I mean, if you start with a symplectic manifold, you don't have to go through this procedure because you don't have a location. Yeah, I think you will get the information of the cotangent bundles somehow. I mean, I don't think if there is something more specific.
But it's not the idea.
No.
It's something knows.
Yes. Yes. It's not the identity. Because one of the things for this symplectic point is that their dimension is 2 times the dimension of M. So you get something patterns. Yes. For a symplectic one, for sure, you get the cotangent model.
And the music that the structure was related to the old one.
the new syntactic structure, the relation to a symplectic structure that you have on the base. It's just that if you push forward using the projection, push forward the syntactic structure, you will get the syntactic structure on the base.
It just becomes just singular experimental locals. So, you have the idea of local moment is like
Local mother of
well,
a singular locus of the Poisson structure. I don't know, but this is well known. This is well known. I mean, there are all these local normal forms for Poisson to manifold or syntactic for manifold.
they were just moving power.
Okay, yeah.
Okay.
But I mean, if you apply to this syntactic groupoid, it will tell me something, because this is kind of well known result.
All right. I think we're here again.